Welcome. Today we're examining a very thorough technical review of the book, Building Event-Driven Microservices. This source material is quite dense, and it's critical for anyone working with modern distributed systems, especially if you're tackling decoupling or managing complex state.
Absolutely. And this analysis, it's really designed for a technical audience, people seeking both foundational and, well, more advanced knowledge in event-driven architecture, or EDA. We should also mention up front that this specific review we're working from was generated by an AI. This was done to ensure we get impartial and really complete coverage of the original book's content.
That's good context. So our mission today is to systematically unpack the key technical components laid out in this review. We'll start with those foundational architectural decisions, move through implementation details, consistency models, and finally, deployment strategies. We plan to proceed carefully and professionally to ensure clarity.
Sounds good. Where should we begin?
Let's start with Section 1, covering architecture, fundamentals, and data structures. That's chapters 1 through 3 in the book. Chapter 1 really hammers home the core concept of aligning microservices. The key takeaway seems to be alignment around business requirements.
That's right. The review points out a common failure: aligning services based on technology, like maybe sharing a database. This inevitably leads to coupling problems down the line.
The material discusses 3 communication structures: business, implementation, like the old monolithic database app example, and data communication. And it highlights that the lack of a robust data communication structure is a fundamental issue, one that event streams are designed to solve.
Exactly. Event streams provide that structure. They enable a clean separation of concerns between the producer and the consumer. The producer writes the data, defines its schema, its content. The consumer then takes that data and builds its own models, its own querying layers, independently.
I find that separation really powerful. The producer's responsibility essentially ends once the event is correctly published to the stream. It doesn't dictate downstream use.
And that concept flows directly into Chapter 2, which dives into the event streams themselves and the core concepts. An event stream is defined here as a durable, append-only, immutable log. Think of it as a timestamp sequence of business facts.
The review contrasts this sharply with older, more ephemeral message passing systems. The key difference being durability.
Correct. This is durable, publish, subscribe. The data persists. It isn't destroyed upon consumption, which allows for reprocessing and building new views later.
The review also details different event structures within the stream. There are unkeyed events, keyed events.
And the key is incredibly important. Keyed events are essential for data locality and for assigning events to specific partitions deterministically. This guarantees order for related events, like all updates for a specific customer ID.
There are also entity events mentioned, which apparently contain the full state of an entity.
Yes, those are important for certain patterns we'll likely talk on later, but sticking with keys for a moment, Chapter 2 introduces copartitioning. This is critical for operations like joins or aggregations across multiple event streams. For copartitioning to work, the streams involved must share the exact same key, use the same mapping strategy from key to partition, and have the identical number of partitions.
So meticulous setup is required there to ensure related data lands in corresponding partitions across different streams.
Precisely. Get it wrong, and your joins simply won't work correctly. The chapter then offers a critique of the Lambda architecture. Its major flaw, as highlighted, is that data isn't written atomically to both the stream and a separate historical store. There are 2 independent writes,
which opens the door to inconsistencies. If one write succeeds and the other fails,
your system state diverges. The review strongly affirms the Kappa architecture as superior for this reason. In Kappa, the event stream is the single source of truth. All other data views or stores are derived directly from that stream, eliminating the divergence problem.
Okay, that architectural context is clear. Chapter 3 then shifts focus slightly to the microservices themselves and the operational overhead. It defines microservices in the familiar way: small, purpose-built, maybe managed by a 2-pizza team.
And it distinguishes between the microservice topology, the inner workings of a service, and the business topology, which describes how services relate to each other functionally.
But then it introduces this concept of the microservice tax. What exactly does that entail?
The microservice tax is essentially the sum of all the costs, financial, manpower, even opportunity costs needed to deploy and operate the required infrastructure.
This includes the event broker itself, container management systems like Kubernetes, monitoring tools, schema registries, and so on. It's unavoidable in a microservices world.
And the key recommendation is to manage this tax centrally.
Yes, absolutely. Centralized management prevents duplication of effort and tooling across many small teams, which can quickly negate the benefits of the microservice approach. The review also touches on the necessary management infrastructure pieces, containerization, CMS, and infrastructure as code, IAC, for managing it all.
All right, let's move into section 2, focusing on the data itself. Data contracts, event design, and integration, covering chapters 4 through 6. Chapter 4 seems foundational, schemas, and data contracts.
They are foundational. Schemas provide that explicit declaration of data structure. They eliminate ambiguity and reduce errors significantly. The review discusses the mechanics of serialization, converting objects to bytes, and deserialization bytes back to objects, noting the schema is integral to this process.
And it compares different schema technologies, Avro, Protobuf, JSON schema.
It does. Apache Avro and Google's protocol buffers are mentioned, alongside JSON schema. An interesting point made is that JSON schema uniquely allows specifying validation parameters directly within the schema, like minimum or maximum values for a field.
But beyond the tech choice, the real challenge discussed is schema evolution.
Correct. How do you change a schema over time without breaking existing consumers? That's backward compatibility. The review highlights a key detail. Deleting an optional field is generally considered a backward compatible change, which might seem counterintuitive at first.
This all culminates in the concept of the data contract. How is that defined?
The data contract is broader than just the schema. It's presented as the formal agreement between the data producer and all its consumers, past, present, and future. It covers guarantees about data ownership, data quality, and, crucially, the rules governing schema evolution.
And it outlines specific steps for handling breaking changes, things that aren't backward compatible.
Yes, a 4-step process is detailed for negotiating a breaking schema change. Design the change, consult with consumers, plan the rollout, and then execute it. The consultation step is emphasized as non-negotiable.
Moving to Chapter 5, this focuses on designing the events themselves for effective decoupling. The main distinction seems to be between state events and delta events.
That's a central theme. State events contain the complete state of an entity at a point in time. They enable a pattern called event-carried state transfer, ECST, and support features like log compaction in the broker. Delta events, conversely, only contain the specific changes that occurred, what was added, removed, or modified.
The review seems quite cautious about using delta events, particularly for communication between different service domains.
Very cautious. The risk is that delta events tightly couple the consumer to the producer's internal logic and state representation. If the producer changes how it calculates or represents something internally, consumers relying on the deltas might break. The argument made is that disk storage is relatively inexpensive compared to the engineering effort needed to debug systems coupled by brittle delta event interpretations. Therefore, prefer state events for cross-domain boundaries.
Are other event types mentioned?
Briefly, hybrid events, which combine state and delta aspects, and notification events, which contain minimal information plus perhaps a URI pointing to the full data elsewhere.
Okay. Chapter 6 then addresses a very practical problem: integrating event-driven systems with existing, often non-event-driven systems, like databases. It starts by warning against the dual-write anti-pattern.
Yes, the dual-write anti-pattern is flagged as highly problematic. This is where an application tries to write data independently to two different stores, say, its primary database and an event stream, without a single atomic transaction encompassing both writes.
Because if one write fails, the systems are instantly inconsistent?
Exactly. You end up with data in one place but not the other. To avoid this, the review details several data liberation patterns. Change data capture, or CDC, is presented as a powerful option. CDC involves reading the transaction log of the source database, like the MySQL binary log.
What are the advantages of CDC?
High fidelity, it captures all changes accurately, including deletes, low latency, and it often supports non-blocking snapshot capabilities for bootstrapping new consumers without locking the source tables.
How does that compare to, say, polling query?
Polling query is simpler conceptually. You periodically query the source database for rows updated since the last check, typically using an updated timestamp column. But it has drawbacks. It increases read load on the source system, and it can potentially miss intermittent state changes if data flips back and forth between polls. It also struggles with capturing deletes cleanly.
And the third pattern discussed is the transactional outbox table.
The transactional outbox is described as a very reliable pattern, especially for achieving at least once delivery guarantees. It works by leveraging the source database's own ACID transaction capabilities. Within a single transaction, the application writes its business data to the main tables and writes a representation of the event to a dedicated outbox table within the same database.
So the business change and the event record are committed together atomically.
Correct. Then, a separate dedicated service or process monitors this outbox table, reads the committed events, and reliably publishes them to the event stream. If publishing fails, it can retry, ensuring the event eventually gets out.
Let's move to Section 3. State, Determinism, and Workflows, Chapters 8 through 10. Chapter 8 tackles state management within microservices.
It differentiates between internal state stores and external state stores. Internal stores are typically local to the processing instance, often managed by a streaming framework, and might be volatile. External state stores are independent systems databases, key value stores that exist outside the microservices lifecycle and are non-volatile.
How do services using internal state recover from failures?
This is where the changelog event stream becomes critical. For internal state stores managed by frameworks like Kafka streams, changes to the internal state are often backed up to a special, compacted event stream, the changelog. If a service instance fails and restarts, it can quickly rebuild its internal state by replaying this changelog stream, which is much faster than reprocessing all original input events from the beginning.
Chapter 8 also discusses effectively once processing. This sounds crucial for things like accurate counts or financial aggregations. How is it achieved?
Effectively, once processing is about ensuring that even if events are delivered multiple times, at least once delivery, the processing logic treats them as if they were processed exactly once. The review notes two main approaches: using transactional capabilities between the client processor and the event broker, if available, like Kafka's transactions, or implementing deduplication logic on the consumer side.
Are there limitations to deduplication?
Yes, the main limitation highlighted is that robust deduplication is typically only feasible within a single event stream partition, where order is guaranteed. Implementing reliable deduplication across partitions is significantly more complex.
There's also a warning in this chapter about data migrations for external state stores.
Indeed. Migrating data in external state stores when the data model changes is flagged as high risk. The potential for inconsistencies during a live migration is significant. The safest approach recommended, although potentially time-consuming, is often to rebuild the external store entirely by reprocessing the immutable source event stream according to the new data model.
Okay, Chapter 9 moves into deterministic processing and the complexities of time. Determinism is key for reproducibility, isn't it?
Absolutely. Deterministic processing means that given the same input events, the processing logic will always produce the exact same output, regardless of when or where it's run. Achieving this heavily relies on handling time correctly. The review distinguishes three timestamps: event time, when the business event occurred; processing time, when the consumer processes the event; and ingestion time, when the broker received the event.
And for business logic, event time is the one that matters for determinism.
Correct. If your logic depends on when events occurred relative to each other in the real world, you must use event time. Using processing time makes the output dependent on the speed and timing of the consumer, which is non-deterministic.
This need for event time leads to challenges like event scheduling.
Yes. If a consumer is processing events from multiple partitions, it can't just process them in the order they arrive at the consumer. Processing time. It needs to buffer and interleave them based on their event time to ensure logically correct processing, especially for time-windowed operations.
What about events that arrive out of order or very late?
Those are significant challenges. Out-of-order events can happen, for instance, if a stream is repartitioned. Late-arriving events are events whose event time is much earlier than the current processing watermark. The strategy for handling late events isn't purely technical. It's often a business decision. Should late metrics be discarded? Should late financial transactions trigger compensating actions? This needs to be defined.
And the safety net here is reprocessing.
Reprocessing is the ability to rewind a consumer's position, offset, in the immutable event stream and replay historical events. It's crucial for correcting errors, testing new logic, or rebuilding state. However, it requires careful planning regarding broker quotas, processing time, and downstream impacts. It's not always a quick fix.
Chapter 10 then focuses on building workflows that span multiple microservices. It contrasts choreography and orchestration.
Right. Choreography is the decentralized model where services react to events independently, coordinating implicitly like dancers following music. Orchestration involves a central component, a manager or conductor, that explicitly controls the sequence of steps in the workflow.
And for handling transactions across services, the saga pattern is introduced.
The Saga pattern addresses distributed transactions, logical transactions spanning two or more independent services or data stores. Since you can't use a traditional atomic database transaction across them, a Saga breaks the operation into a series of steps. Each step commits its own local transaction. Crucially, each step must also have a corresponding compensating transaction that can undo its effects if a later step in the Saga fails, effectively rolling back the distributed operation.
Is there tooling suggested for managing these complex workflows, especially for orchestration?
Yes. The review mentions the concept of a durable execution engine, DE. A DE is a platform specifically designed to manage and execute long-running, potentially complex, orchestrated workflows. It ensures that the workflow logic progresses and eventually completes, persisting state and handling retries, even in the face of intermittent failures of individual services or network issues.
Now we arrive at the final section. Implementation frameworks and deployment, covering chapters 11 through 14, plus chapter 21 on deployment. Chapters 11, 12, and 13 compare different implementation options, starting with basic producer-consumer BPC.
BPC options, covered in Chapter 11, provide the fundamental publish-subscribe capabilities. They're often simpler, but may require developers to manage state externally more explicitly. The sidecar pattern is also mentioned here, using a separate process alongside a legacy application to add event-driven capabilities without modifying the core legacy code.
Then there are heavyweight frameworks in Chapter 12.
These frameworks, like Apache Spark or Apache Flink, often have origins in large-scale data processing and analytics ETL, complex windowed analysis. Historically, they required dedicated clusters, which could sometimes complicate independent scaling of processing resources compared to storage or broker resources, though this is evolving.
And Chapter 13 covers lightweight frameworks.
Lightweight frameworks, with Kafka Streams being a prime example cited, rely primarily on the event broker, like Kafka, and a container management system, like Kubernetes. They don't need a separate processing cluster. State management is often handled internally using techniques like ROC's SDB, backed by changelog streams for fault tolerance. Shuffling data between processing stages is typically done using internal event streams within the broker itself. Recovery often involves using those changelogs and potentially maintaining hot replica instances for faster failover.
Chapter 14 introduces streaming SQL. How does that fit in?
Streaming SQL, offered by platforms like Flink SQL or KSQLDB, provides a higher-level declarative way to process event streams. It leverages the concept of stream table duality, treating streams as continuously updating tables. You write a SQL query that runs continuously, processing events as they arrive and dynamically updating the results.
Does it allow for custom logic beyond standard SQL?
Yes, the review mentions the use of user-defined functions, UDFs. These allow developers to embed custom code, for example in Java or Python, to perform operations not available through built-in SQL functions, extending the platform's capabilities.
Finally, Chapter 21 addresses the critical operational aspect, deployment patterns.
Deployment is where the architectural and design choices meet reality. The review stresses prerequisites, ensuring the new version meets service-level agreements, SLAs, minimizing dependencies on other services changing simultaneously, and carefully negotiating any breaking changes with consumers beforehand.
What are the main patterns discussed?
The full-stop deployment is the simplest. Stop the old version, deploy the new one, restart, but it involves downtime. The rolling update pattern avoids downtime by gradually replacing old instances with new ones. This works well if the changes are backward compatible and prerequisites are met.
What about deploying breaking schema changes specifically?
That's treated carefully. 3 variants are outlined: deploying the change to the same stream, deploying to a completely new stream, or writing to both streams in parallel during a transition. Variant 2, writing to a new stream, is often highlighted as safer because it prevents the new schema from potentially causing silent failures in older consumers still reading the original stream. However, it requires careful management to ensure data isn't permanently divergent if the migration isn't fully completed.
And the blue-green deployment pattern.
Blue-green is presented as a robust strategy for minimizing downtime, especially for complex or risky changes. You stand up an entire independent copy of the service or system, the blue environment, running the new version, parallel to the existing green environment. Once blue is fully tested and verified, you reroute live traffic from green to blue. This provides an immediate rollback path if issues arise simply by switching traffic back to green.
So we've covered a lot of ground, tracing the key technical insights from this review, from foundational ideas like the data contract and Kappa architecture, through practical integration with CDC and the outbox pattern, state management, determinism, and finally, specific implementation frameworks and deployment strategies.
It's a comprehensive look. I think the fundamental message that comes through is that building reliable, event-driven microservices requires a deliberate investment in the data communication layer. Get the data definitions, the schemas, and the event design right first. And the preference for state events for cross-domain communication seems like a strong recommendation for maintaining long-term decoupling. Of course, for a truly deep and actionable understanding, we strongly recommend you read the full book itself. The review gives the highlights, but the source material provides the depth.
That's an excellent point. Thank you for joining us for this analysis of these complex but crucial patterns in event-driven systems. If you found this discussion helpful, please do subscribe to our channel for more detailed technical reviews like this one. We wish you a great day.